Good morning, everybody. My name is Akio Kasuga from Tokyo. I'm basically bridge engineer of the construction company. So the Japanese construction company is a little bit special because we have a design department. I belong a long time for the design of the bridges. And also we have a R&D center. And I also developed many new technologies for the bridges. So today, my presentation is very practical, and it's covered from the material to the end of life. So I hope my presentation will help for the next generations getting some clues to the carbon neutrality of concrete structures. So this is the contents. I will show what we can do now for the carbon, low carbon with the structure, and also we should act immediately for the future. And this is the two themes, including in my presentation. So this is a very famous article by Guardians in 2019. At that time, and I've been belonging to the FIB so long time, and we discussed a lot. So now, at that time, the flight shame, but compared with the airplane, the construction CO2 emission is so large. So the next time is the concrete shame, something. So we have to prepare something. And I was the president of FIB from 2021 to 2022. And the beginning of 2021, we launched the official statement to the public what we did for a long time. I mean, the Model Code 2010, we included sustainability, and now we launched already Model Code 2020. The sustainability is the center of the Model Code. But this is a fact. Concrete emits CO2 a lot, but mostly the CO2 comes from the energy. But as a structural engineer, we have to lots of things to solve this problem. And at that time, I asked the secretary is in the EPFL, and how FIB is a structural concrete society. So all of the cement, how much cement we use in the structural concrete. Fortunately, they have the data. 2015, and about 60% of the cement goes to the structural concrete. So many. And after that, we think about how to solve this problem. So we discuss a lot among the FIB society, and I use this supply chain European standard. It's very understandable compared with CDP and SBT. I'm from a construction company, so mainly the builder have the responsibility to reduce CO2 in A4, A5. But the most of the emission CO2 come from the material A1 to A3. And the rest of the CO2 come from the use stage. So I checked the Japanese data, and I show you the $1 million per $1 million we emit 400 tons CO2, and in the use stage 600 tons per $1 million, because my company is a construction, not only the infrastructure, but buildings. So the buildings emit the CO2 in the use stage. And especially talking about infrastructure, A1 to A3 is 400, and B1 to B3, B4, B5 is about same. So I will show you the later. So the most of the CO2 emission come from the not construction companies scope 1 and 2. So the materials is scope 1, 2 of the suppliers, and the use stage should reduce the CO2 by the owner of the building or infrastructures. So I thank you, Dr. Collins. This is very, very useful database I use a lot in presentation in Japan. So this diagram shows the CO2 emission is independent from the size of the construction. So it is the same, the million pound, each million pound emits CO2 about 400. So the $1 million and 100 million yen, almost the same, about the 400. 400 ton is very, very useful in index for the practitioners to make some strategies to reduce the CO2 of the construction industry. So 400 ton CO2 per million euro per million pound per 100 million yen. It's the same as the developed countries, but developing countries, we did a lot of projects in Southeast Asia. It's about 2 times, 3 times, 800, about more than 1,000. It makes sense because of the consumer price is cheaper. So this is a very, very conceptual diagram of from the material construction and the use stage. And in Japan, we discussed a lot of CO2 emission by the materials, but at the same time, as I said before, in the use stage B, they emit the CO2 because the maintenance is the construction, the same. So now we don't have any database in the use stage. In the FIB, we have started to collect the data like a database of the bridges, as I showed before, in the maintenance stage. It is very important to reduce the CO2 strategies. So ideally, after the reduction of the CO2, we reduce the CO2 in the material in the construction and also the use stage like this. And at the same time, I checked any industrial data of the Japanese CDP database. The construction is, as I said, scope 1, 2 is very small, and the scope 3, I mean, from material from the use stage is dominant, about 98%. So it makes sense. The finance is very small because they use only the electricity something, and also the aviation, the transportation, they emit the CO2 in scope 1 and 2. It makes sense. So it is not so easy to reduce CO2. Some aviation companies use biofuel, and also the manufacturing electricity, they use a lot of CO2 in scope 3. So maybe the tendency is the same in Europe and any other developed countries. Anyway, the construction emits CO2 in scope 3. Okay, so how do we reduce CO2 by using the useful, at this moment, technologies in the material stage, A1 to A3. I'll show you the example. And in my company, we already have zero cement concrete by using a byproduct, silica hume, and blast furnace slag, and fly ash. And so theme of this IABSE is the emergency action. So by using this byproduct, we can reduce CO2 a lot, up to 70%. And fortunately, the strength of this concrete is more than 100 MPa. So we can use this material to the structure of members. And this material dry shrinkage is very small, and creep is also very small, about 1/3 of the conventional concrete. And also somebody says that mixing water can be reduced about half compared with the conventional, which means in Japan we use drinkable water for the mixing in the concrete. So we can reduce the water by using this 07 concrete. And stage B, and use stage, as you can see, the problem of the maintenance is deterioration of the sea reinforcement. And of course, in Japan, we use de-icing salt during winter, especially highway. They deteriorate reinforcing bar, sometimes processing steel like this. And also deck. And our highway was built more than 60 years ago. And heavy traffic, and also using by de-icing salt. Now we are replacing the reinforcing concrete to the processed concrete. We use a lot of money, about 4 or 5 times compared with the initial investment of the highway. So, in order to avoid this, we cannot use the steel reinforcement. So we had a project with a highway company since 2010 by use the plastic fiber as a tendons. And of course, this concrete is expensive. We can reduce the weight of the superstructure. We call it a non-metallic durabridge. And at that time, the highway company asked us, the initial cost is 50% expensive. Compared with the maintenance cost, they said it sometimes is 2 times, 3 times, 4 times something. So 1.5 times is the reasonable for them. So at that time, we had technologies to use aramid fiber for the tendons. Because of the 30 years ago, we focused on this new material to the Maghreb. But unfortunately, it is very expensive at that moment. But now we have a fiber reinforced concrete, so we can reduce the initial cost up to 1.5. And in 2020, we built the non-metallic highway bridge in Tokushima Prefecture. The span length is very short, 25 meters. And it is completely segmental construction. And you can see the yellow tendon is aramid fiber. And in the butterfly, we call it the butterfly web, is only 15 centimeter thickness, no reverse, of course. And we use external tendons in the right-hand side photos. At the same time, as I said before, we now had the replacement of the deck, so many bridges. And the highway company tried to use non-metallic technologies in this deck replacement, non-metallic deck. And in this project, we use polyvinyl fiber in the deck. And not only the transverse direction, but the longitudinal direction, we use aramid fiber, both directions. In 2021, we already built one non-metallic deck replacement, and we expect the non-maintenance of the structural members, but of course accessories that they have to replace in the 100 years lifetime. But basically, including the concrete barrier, we didn't use any steel reinforcement and the tendons, so it may, I hope, the no maintenance during lifetime. So they can reduce the maintenance cost a lot, which means at the same time the CO2 emission during use stage B. So finally, my company has 7 concrete factories in Japan, and one of them we replaced the very short trial meters processing pretension beam made by the zero cement concrete and aramid fiber in 2019. So this is the first completely zero cement low carbon beam. And of course, we can use mixed water and seawater because there are no deterioration materials inside of the beam, somebody says. So in the factories, we can provide this new material, but our wall is, the price is about 2 times, 3 times compared with conventional concrete, and also sometimes the client don't want to pay. So this is another problem, but as you know, the Japanese carbon tax is very low, about $3 something. But I know that Europe, the carbon pricing is much larger than that. So it's the compensation between the tax and the price of the new material. We try to calculate by using Ashito girder and conventional material, and also zero cement concrete and aramid fiber. And this is a result. In the material stage, we can reduce 60% of the CO2. And also, I use the scenario of the lifetime by the Indiana, United States. It's very convenient. And finally, we compare with conventional and low carbon bridges in life cycle assessment. So the stage A, B, C shows that we can reduce 82% reduce 82% CO2 by using the present material and low carbon technologies. So we can do that. We can do now. But as I said, we have some very high walls to use this. Okay, I calculate this reduction by using carbon credit, for example, 150. This reduction means about $270 per cubic meter. So we can call this green premium mentioned by the Bill Gates in this very famous book. Okay, so another way to reduce the CO2 is lighter structure. And it is highway extrude with butterfly web. We design in a detailed design. So compare with the basic design uses conventional box girder type. In this project, the most difficult condition is the width of the pier at the river. So its maximum is only 5 meters. So everything is concentrated. I mean, the right-hand side piers should carry the most of the force during earthquakes. So we reduce the superstructure, and we make flexible the all piers at the same time. So finally, we can reduce the earthquake force during earthquake. Then we can reduce the weight, superstructure 20%, and CO2 emissions, especially the substructure, we can make it half. So we do right now by using these technologies. The lighter structure result, the CO2 emission are very low. Okay. We have to think about dismantle and reuse, as you discussed before. So this is one example, the building, precast building by using unbonded tendons, and it is very easy to dismantle. And especially the room is a modular type. We can reuse, recycle this modular type room, and also dismantle and check the factories and make it like a virgin material, we use another project. So which means that we can reduce the CO2 in stage A. So some Japanese economists criticize that carbon neutrality shrinks the economy, but I don't think so. So in this case, we can make a new market like reuse of the concrete members. It's a auction market. But in Japan, we have already the auction market of the timber. I mean the monolith timber. It's a very long time. And the famous Japanese carpenter says if the 100 years old timber, they can survive 100 years, 1,000 years, 1,000 years. So we can do that in the concrete structures. The new market, we can make it. And also, this is the responsibility for the concrete structure engineers. Okay, another thing is we should act from now. In maintenance process, we don't think about the influence of the society, but if we can reduce the construction time in the maintenance process, we can reduce the CO2 a lot. I mean, it's indirect CO2. Fortunately, we have a data from Germany. It's the Beton calendar data. And the horizontal axis is the construction time, 1 month, 2 months to the 2 years in the right-hand side. And the vertical axis is CO2 emission. You can see from 6 months, the indirect CO2 is larger than the direct CO2. So if the construction time is 2 years, about 80% emit CO2 come from the indirect. I mean, the congestion, the traffic, and any other influence to the society. This is very, very interesting things. We never think about this, but from now, we have to think about this kind of the indirect CO2 emission by the maintenance. Okay, another thing, and during the use stage, as you know, we have in Japan we have earthquakes and also many rains in the rainy seasons. And for example, if the event occurs, that we have to reconstruct and after the disaster. But we spend very small amount of money before that. I mean, it's resilient. It is make resilient the structure. We can reduce the reconstruction very, very much. This is a report from the Japan Society of Civil Engineers. I'm sorry, this is a Japanese yen, so please divide it by 150, 190 something. So this is the earthquake in the metropolitan area, Kanto earthquake. So it's been a time, the last time was more than 100 years ago. So we lose 855 trillion Japanese yen, very, very much money. But we spend the resilience cost about 10 trillion yen. We can save the money to 273. It's about 34%. So only 10 trillion saves money, more than about 300 trillion, which means the problem in Japan, the financial Ministry of Finance, they said we don't have any money. So the recovery after disaster is construction. Construction means emit the CO2 a lot. So in order to do this, make resilient, we ask the private investor, okay, this is ESG investment, and we can return a lot of money. So this is very important for, especially Japan. So now I'm the executive fellow of the company. So I withdraw the front line of the management of the company. So I have sometimes. So from the April, I am the principal senior researcher of the University of Tokyo to do some government project. So it is to launch, to install our technology to the society. So one of the projects is to especially the local government of Japan, they don't have money to maintenance of the bridge. So in certain cities, they have 800 bridges, and some of bridges very important, but it's very old, deteriorated. So we simulate if this bridge closed, and east side is the industrial, and the west side is a city. The city people and the industry, the company, they lose a lot of money. We can simulate this kind of event. And we collaborate with the financial people to make a scheme as ESG investment, such a kind of event. So carbon neutrality, we have to do a lot of things, not only the technical things, that she said before. We have to talk, we have to discuss with financial people. So in FIB, as you know, we are the members from the supplier, builder like me, and owners of the infrastructure, the building, and also the construction company. Many players. But the FIB now discussing, and this is a roadmap compared with the 2020, and we reduce 50% by 2030 in each stage. So as a construction company, we focused on not only the A4, A5, but material and also the use stage like this. So this is the target. Okay, this is the conclusion. And especially, this is a message to the young engineers. So the carbon neutrality is a new value. And it is very important, carbon pricing. And unfortunately, Japan is a very low price. And everybody think about, everybody says that carbon neutrality, new low carbon materials is cost. But we should pay all of the people in the world. And the A1 to A3 by using a byproduct, it's a transition up to I don't know when, and the zero carbon cement, zero carbon steel realized in the society. It's a transitional way, but some clients asked us, you should do immediately, but without any solutions, we have to disappear from the bidding. So it's a very serious situation now. And in the use stage, we should use ultra durable technologies. And also studies the relation between the durability and the CO2 emissions is lack of data, so we have to collect this kind of data right now. And resilience is very important to reduce CO2, not only the deterioration, but the disaster. So that this morning, Russia has a flood. The flood occurs everywhere in the world. So we have to think about how to resilient the structure produced by the engineering smart knowledge. Thank you for attention.